Okay, today what I'd like to do is talk a little bit about CNC turning. Remember, we talked CNC as computer numerical control. Prior to CNC, there was such a thing called numerical control. Back in the 70s, and I think CNC started at MIT, numerical control was what they called point-to-point programming. So instead of having a computer figure out all the moves and all the radii and all the blends, and so to speak, you actually had to program point to point. That was NC programming. So on a CNC lathe, you can do turning, you can blend radii, and I'm going to power this CNC lathe up in a second. And we have a computer-controlled device, or CRT, that I'll be able to show you the program, and I'll be able to show you the resolution and the offsets we talked about earlier. We're actually going to machine a brass coolant ball. When you machine, and you'll see this not on this operation, but on a milling operation that we'll talk about, you have coolant. And coolant is either oil-based or water-based. And there's a whole industry that sells and manufactures coolants for manufacturing, which is a whole other career set as well. But we take raw brass, and we're going to machine this coolant ball, and it's pretty simple. It's a I believe a 5/8 diameter piece of brass. And we're going to put a radius on the front, a diameter on the middle, and then a radius on the back side. And then we're going to drill a hole and tap a hole. You probably know this, but tapping a hole means you put a thread on the inner diameter, ID. So that allows us to thread in a copper tube if we want to direct the coolant a certain way. But this is the part we're going to make, and up here is a tool holder that the coolant ball actually goes into. So I'm showing you the actual application of how it's used. I think it's important that if you don't understand in anything, in manufacturing or in engineering or just in general life, if there's something you don't understand, don't seem to think that it's silly to ask a question. It's only silly if you don't ask the question, because you really do need to understand, and each concept you understand will get you to another higher level. So give me 1 second, I'm going to turn the machine on. The machine runs off of, this particular machine runs off of 230 volts, 3-phase. In order to run a machine, you also need to have pneumatics, air supply. So this particular machine also needs air. The bar stock is held by a collet, C-O-L-L-E-T, collet. And so it closes to hold on the bar. Well, it has to draw back to do that. So pneumatics or hydraulics will operate that. So hydraulics use hydraulic fluid, pneumatics uses air pressure. So that's why you need air on this particular machine. And sometimes you can use an air purge to keep things from getting contaminated. So there's all sorts of different applications of electrical. Of course, the machine is electrically powered. Pneumatics, the collet closer is pneumatically operated, and sometimes you have air blasts. And then hydraulics. This machine doesn't have hydraulics, but many machine tools do. So the computer will power up, and it has to go through a homing sequence and an initialization, just like a computer at your house would have to do. Notice when I hit reset and I held up the E-stop, that the machine started doing a little bit of a movement and a sequencing to find position. So the first thing I'll point out is that you'll see you have 1, 2, 3, 4 leading positions. Remember I said 10 millionths would have 4 leading zeros and then a position after that. So this will show you that it has the resolution or tool offset capability in 10 millionths increments. So what I'm going to do is I'm actually going to cycle the machine and talk about the operation, and then we'll show you a close-up also in a different shot. So you can see the Z position, you have axes on a lathe. Z is length and X is on diameter. So in this particular part, diameter is on the OD, and length is on the length of the part. So this is Z and this is X. Now there are other axes. On milling machines you'll have at least 3 axes. And on grinders you'll have 2 or 3 axis minimum. And then different machines will have multiple axes. So that's how long it took us to make a part. Remember I said everything's very literal in manufacturing. When you make a part, it's caught. They call that a part catcher. It's very simple. For example, when the chips, some machines have a conveyor that takes the chips out. Guess what that's called? A chip conveyor. A lot of these definitions are very literal. When you have bar stock in the machine, you have a bar that you need to feed. Guess what? That's called a bar feed. These are not very difficult terms. The unit inside the machine, inside the lathe, spins and it holds the part. That's called a spindle. Once again, very literal. When you cool the part and cool the tools, the fluid is called coolant and the lines are called coolant lines. When you need higher pressure on a lathe to keep the part cool and the chips cool, that's called high pressure coolant. So these are all terms that really aren't that difficult. So hopefully I'm conveying that almost anybody that has interest can really do well in manufacturing. Okay, what we're going to do right now is we're going to cycle the CNC lathe, making a coolant ball out of brass, and I'll describe the operations as it's going through its sequence. We're going to center drill so that the drill doesn't walk when we go in with the drill. And you can see the brass chips coming out of the ID. Now we have a tap that we're going in. It's a self-releasing tap holder. So we'll reverse the spindle so it'll be able to be taken out. Now we're going to face the part, do the lead radius on the front side, then a straight diameter, then plunge a groove, and then back turn with the other side of the insert, the other radius, and then we're going to cut it off. Now the last operation, the collet is now open so that we can, if we had a bar feed, we would feed the bar out to that stop. But right now it's a manual operation. So let's talk about materials. This is brass. Brass is defined as free machining. Brass is very easy to cut. You can actually cut it dry because the tools can withstand cutting the brass very readily. But what you'll know is that there's all different materials. For example, this prop shaft, the stainless will not rust. So anything that's in water or anything that's in the food service industry has to be made out of stainless. So stainless is very hard to machine, much harder to machine than brass. This is a part that we talked about earlier. It's for a hard drive in an IBM computer. Aluminum and stainless steel, both in the same part, actually combined. Aluminum is also very easy to machine. In the aerospace industry, there's a material called titanium. Those of you in chemistry and have been in chemistry class, you look at the periodic table. You'll be able to see a lot of these materials show up. Aluminum, you'll see that. Copper, you'll see that. And each one has a different functionality in terms of machining, either easy or difficult. Titanium in the aerospace industry is very strong, but it's also very lightweight. So when you're going up in the air in aerospace and commercial airliners and whatnot, you want something that's lightweight, but you also want something that's very strong. Aluminum is also very lightweight and also very strong. So there's a lot of aluminum and titanium in airliners and in jets. So right now we're going to talk a little bit about milling. So over here, let's talk about something that touches almost everyone's lives, and we're going to talk about computers. And we're going to talk about this particular computer right here is a MacBook Pro, to be exact. And this video that I'm going to show shows a solid piece, they call that a billet of aluminum that's very flat, and if you recognize the shape, it looks not too much different than the keyboard of the MacBook Pro. So I'm going to push play here for a second. What you're going to be able to see is a milling machine. Remember, we called this an end mill, and you can see all the aluminum being cut, the chips. And then you can see the coolant that's cooling the tool and the part, and you can start to recognize right there, that's the keyboard on the MacBook Pro. So if you look at that, and if you look at this MacBook Pro, you'll look and you'll recognize they're one and the same. In fact, if you hold it this way, you can really see it, because you can see where the mouse pad goes, and you can see the exact keyboard. All right, so let's go back and talk about tolerancing one more time. Let's circle back to that. Remember I said that a human hair is 3.5 thousandths. When you have a 5 here, that represents half, because the function is that 10 is a full digit to the next denomination. So when you see a 5 there, that's a half. So if that's 3.5 thousandths, you'll see 2 leading zeros in thousandths, and then a 5. That represents 3.5 thousandths. So that's the diameter, remember, OD, outer diameter, of a human hair. A lot of these tolerances on the MacBook Pro in milling will be in thousandths of an inch tolerances, maybe even tenths. A lot of these tolerances on something more accurate, for example, if you have something where a bearing might rest, that might be plus or minus 1/10,000th of an inch. And that could be done on a lathe, or it might have to be done on a grinder.